Hello everyone, my name is Hao Lin. I'm honored to present our work titled UniAP, Unifying Inter- and Intra-Layer Automatic Parallelism by Mixed Integer Quadratic Programming, which has been selected as a CVPR 2025 award candidate. This research was jointly conducted with Wu, Jie Li, Jun Li, and Wu-Jun Li. In this work, we propose UniAP, an automatic parallelism method designed to accelerate the distributed learning process. For example, when training VIT-Huge on 8 Titan XP GPUs, UniAP optimizes the parallel strategy within just 1 minute, achieving a 1.4 times speedup in training throughput. Similarly, when training Llama 7 billion on 8 A100 GPUs, UniAP completes strategy optimization in 36 seconds, resulting in a 3.8 times throughput speedup. The presentation will be structured into 4 main sections: introduction, method, experiments, and conclusion. Modern distributed learning systems support a variety of parallel strategies, which can be divided into 2 categories. Inter-layer parallelism, such as pipeline parallelism, partitions the model into disjoint sets without partitioning tensors in each layer. Intra-layer parallelism, such as data parallelism, tensor parallelism, and fully sharded data parallelism, partitions tensors in a layer along one or more axes. Beyond these parallel strategies, we define parallel method as adopting a single parallel strategy or a combination of several parallel strategies within a specific system. Parallel methods can be classified into 2 main categories: manual parallelism, where users manually select and optimize strategies based on domain knowledge; automatic parallelism, which automates the optimization process. Now, let's explore the motivation behind our work by addressing the question: why automatic parallelism rather than manual parallelism? Manual approaches demand extensive domain expertise and are often inflexible when applied to different models or hardware setups. Even experienced users face challenges in selecting effective strategies. We conducted a case study on the candidate parallel strategies of Llama 13 billion. Results show that it is rare to find a trainable configuration. What's worse, it is easy to suffer at least 29% of training throughput loss by missing the fastest trainable parallel strategy. Thus, we need AP methods. We now turn to the second key question: why UniAP rather than existing automatic parallelism methods? Current AP methods typically fall into 3 categories. First, interlayer only AP, only considers PP. Second, intra-layer only AP, focuses solely on DP, TP, FSDP, or their combinations. Third, hierarchical AP, they first optimize part of the strategies, for example, interlayer parallel strategies, and then optimize the left part with the former part fixed. What's missing is a method that can jointly optimize both inter- and intra-layer parallelism strategies in a unified manner. This motivates UniAP, which jointly optimizes both types of parallelism, leading to globally optimal solutions. UniAP's overall workflow consists of 4 main steps: profiling runtime information for both hardware environment and model, then build time and memory cost model to estimate costs. After that, we transform the parallel strategy search into a mixed integer quadratic programming optimization problem. Last, we iteratively apply the cost model and MIQP across different configurations in unified optimization process, determining the optimal parallel strategy. In the profiling stage, we gather critical performance metrics from both the hardware environment and the model itself. For the hardware environment, we mainly profile P2P communication efficiency and or reduce efficiency between GPUs. For the model, we profile forward propagation time for each layer and memory cost including activation, parameter, gradient memory cost, and so on. This profiling data serves as input to our cost model, enabling accurate estimation of training costs under various parallel strategies. We also build two cost models, a time cost model and a memory cost model. The time cost model estimates forward propagation time per layer under each parallel strategy, while the memory cost model estimates memory consumption per layer. The two cost models allow us to estimate the total training time and memory footprint for any given parallel strategy. The objective function is the heart of the MIQP formulation. Our goal is to maximize the training throughput, which is equal to minimize the time per iteration, abbreviated as TPI. In distributed learning, time per iteration is determined by the critical path in pipeline execution. In the example below, we select G-pipe-style pipeline parallelism, where the critical path is illustrated by the purple arrows. Then, let's walk through a set of constraints using a concrete example. Suppose that we have a 3-layer model G being assigned to 2 pipeline stages. Each layer selects one of several possible intra-layer parallel strategies and is mapped onto 2 physical computing nodes. The computation stage constraint models the total time cost for a single computation stage. For instance, in the candidate solution, time cost of stage 1 equals to latency of layer 0, layer 1, and latency between layer 0 and 1. Similarly, time cost of stage 2 equals to latency of layer 2. The communication stage constraint accounts for communication overhead between training stages. In our example, the time cost between stage 1 and stage 2 corresponds to the inter-layer stage communication latency. The layer placement constraint guarantees that all layers should be placed on exactly one pipeline stage. Furthermore, each pipeline stage must contain at least one layer to fully utilize computing resources. The order-preserving constraint ensures that the original order of layers is preserved across pipeline stages. In other words, if a model has 3 layers, they must be placed to pipeline stages consecutively. You cannot place layer 0 and 2 on stage 1 and layer 1 on stage 2. The strategy selection constraint ensures that each layer must and can only choose exactly one intra-layer parallel strategy. Finally, the memory constraint ensures that no device exists its available memory capacity. In the example, we ensure that both stage 1 and stage 2 fit within the memory limits of their respective nodes. By combining these constraints with the objective function, we fully define the MIQP optimization problem, enabling joint optimization of inter- and intra-layer parallel strategies. However, there are additional hyperparameters in pipeline parallelism that also impact performance, the pipeline degree, and the number of micro-batches. To account for this, we perform an enumeration over these hyperparameters in the unified optimization process, invoking the MIQP solver for each combination to identify the globally optimal parallel strategy. We select Grabi as the MIQP solver and evaluate UniAP on 2 key metrics, training throughput and the strategy optimization time. On NVIDIA GPUs, we compare UniAP with SOTA AP methods including Galvatron and ARPA. Our results show that UniAP achieves up to 3.8 times training throughput speedup compared to them. In addition, UniAP reduces strategy optimization time by up to 107 times. These results demonstrate both performance and efficiency gains in UniAP. When applied to non-NVIDIA devices, such as high-end DCUs, we compare UniAP against popular manual parallelism methods like Magnetron and DeepSpeed. Results show that UniAP can find the fastest parallel strategy while spending less time for strategy search than Magnetron. Notably, DeepSpeed fails to provide feasible solutions in our experiment. These results highlight the robustness and generalization capability of UniAP across diverse hardware architectures. To further validate the effectiveness of UniAP, we conducted several additional experiments. Our scalability tests show that UniAP scales well with increasing number of devices. Our ablation study confirms the importance of jointly optimizing inter- and intra-layer parallelism. In summary, we propose a novel AP method called UniAP to unify inter- and intra-layer AP by MIQP. To the best of our knowledge, UniAP is the first parallel method that can optimize the two categories of parallel strategies jointly rather than separately to find an optimal solution. Experimental results show that UniAP outperforms state-of-the-art methods to achieve the best training throughput. We believe this work opens new directions for efficient and scalable distributed learning. Thank you for your attention. If you are interested in this work, please visit our personal website and reach out to us.